WIN2021, and this is the Lecture Week session part 1. We have, to start out, we have Andrea Wulzer from Padua, who will tell us about electroweak precision potential of the HLLHC. And I would just like to remind everybody, please, if you have questions, post them on Q&A, and then I'll ask them at the end of the talk. So go ahead, Andrea.
Okay, thank you very much. Thank you very much to you and to the other organizers for the invitation to give this theory overview talk at this nice workshop, the overview of the week session, of course, which I will do. But as you see from the title, I also want to spend some good fraction of my time speaking about somewhat more specific topic, which, as you see, has to do with the potential of the LHC and its high luminosity extension to probe the electroweak. But actually, electroweak plus Higgs plus top, nowadays these things all go together, sectors by precision measurements. And the reason for doing so, there are two reasons. One is that I think this is a subject that is receiving increasing attention, and I see also experimental papers devoted, for example, as I will speak about, to effective field theories studies related with this topic. And so it's important, it's a subject that deserves development. It's one of the many interesting subjects that one can study at the LHC and the luminosity LHC. And second, because I want to convey the message that there are a lot of things that we can do exploiting the LHC and in preparation for the high luminosity LHC, which is not that far in the future if you compare with the number of things that you would like to see and studied and understood before the data come. And the best way to convey this message, I think, is also to be specific on something that I find interesting. Now, so, but of course, fortunately, the topic of this electroweak session and this conference is much more broad than this. So let me start with some more ideological words concerning the role of high energy physics in the landscape that I see in front of my eyes today. And it's not this, I mean, I think it's the same landscape we have in energy physics and in the whole landscape of fundamental physics. It looks to me like an ocean, which is an ocean of opportunities. And on an ocean, what you can do is that you can sail in some directions, which are outlined here by these question marks. And these question marks correspond to the open questions that we have about the physics of fundamental interactions, the questions that standard model, which is our best friend and our best enemy, cannot address. These questions are clearly fundamental and pressing question. Each of them, I'm sure, will find a solution, or in some cases we'll have to find a solution because it's very much observational, right, driven. But the way in which we can exploit these questions is by postulating possible solutions, which we call beyond the standard model scenarios or models. And once you have a model or a scenario, then you can go back to the ocean and identify a direction where to sail in order to see the manifestations of this scenario, without guarantee that this scenario you have in mind, the model you have in mind, is the actual one that is addressing this problem, nor typically having a guarantee that you have enough steam to sail far enough in this direction. Even if there is land, you may not reach it. And this should be contrasted sharply with the shape it had, energy physics in my mind when I was a PhD student, which looked very much like a road, which was paved of these W boson topics that we can call theory anticipated discovery, or at least strong theory guidance. And the strongest form of this guidance for these three items here goes in the form of what we call no-lose theorems, like the Higgs no-lose theorem that was obliging for mathematical certitude the LHC to discover the microscopic origin of the masses of the mediators of the weak interaction, right? The Higgs could have been the Higgs, could have been something else, but it must have been something. And then it was understood that this path would have continued with scenarios addressing the so-called naturalness problems, such as supersymmetry. This didn't happen, and what we have today, and the situation will definitely change the next discovery coming from the LHC or from the luminosity LHC or from other experiments. I'm sure the next sharp discovery of a new fundamental law of nature will put us back on some road. But nowadays, the standard model, as you know, is a potentially complete theory in terms of theoretical terms, and its incompleteness does not show up, as I just discussed, in a way way that can sharply outline one new direction, one new road where necessarily we're going to discover new physics. So particle physics is not validation anymore. The key word is exploration of unknown territories, which is great because it means that the next discovery coming from particle physics or not will, no matter what, be much more revolutionary than the discovery of the Higgs, for example, or of the top, because it will be unexpected. So will change the way we understand nature much more radically. So the colliders are great tools for exploration, taking into account that no single experiment or facility or device can explore all these directions, all these question marks at once. And even if it did, we know, okay, as I already said, that we cannot even be sure that even if you look to all models beyond the standard model in the archive, one of them, not even a single one, is the right model. Maybe the reality is something we have not yet thought about. This is actually very likely. So no one can guarantee discoveries of new fundamental laws of nature. And in this context, then, high energy physics is one of what we call the frontiers. Maybe 30 years ago, I don't know, was the frontier. Now it's one of them. But it's the one that is directly looking at what we care about, which is short distance physics laws, as short as we can, of course, with accelerators. Directly here means that you can have access to the new particles that correspond to this that show up in these microscopic worlds, or you can have access to directly by producing them, or you can have access to them, as we also say, indirectly, but still by the effect that they have on cross sections, but still you are directly probing the new short distance law, which is induced by these new dynamics, maybe taking place at masses or energies which are even which are even shorter, right, than the one you can probe. Should also be taken into account that when we say that the colliders are exploring one single frontier, which is the energy frontier, well, it's true, but on the other hand, the same mechanism, the fact that particles may be too massive to be seen until now, because energies until now have been too low, such that if we raise the energy, we can discover them, can actually underlie plethora of possible signatures of these particles. And so one collider corresponds to 1,000 searches, as we call them, or 1,000 experiments inside the watch single collider, which have each one their own opportunity, which is needed to be exploited and explored to characterize this energy frontier. It's also true that high energy colliders do have a guaranteed outcome because we do have high quality, precise, if you want, data collected under simple enough conditions to enable precise standard predictions. And these predictions use directly the principles of quantum field theory, which to us are even more fundamental principles than the standard model is, okay? But on top of this, we do have the standard model that enables concretely these predictions. So one clear thing that we can do with this data is compare data with predictions, which after all is the job of physicists. This point also outlines the effectiveness of our exploration, okay, of the exploration of the unknown, can be robust and conclusive. And furthermore, the questions that we can pose, so we have to keep this attitude of exploring, right, the unknown in a way that is as much as possible independent on the questions that we think are relevant, but we can also, and we should also ask some of these questions the way in which they are interpreted by these beyond the standard models. And this we can do in a very precise way because we can phrase the BSM questions in an extremely precise way, again, using quantum field theory, right? So when I'm asked to speak of future colliders, right? I always say that I have no clue I have no way to explain why we should build a future collider, because to me it's totally obvious, okay, that I would like to be able to do physics with such a machine. We can discuss why not to build such a future collider, and one good reason could be that future colliders tend to be typically expensive. So we have to be so aware that we are extremely lucky that we have one such collider running, and that we keep running. This is the LHC, and its high luminosity extension will keep running over the next 20 years, which of course, I mean, in normal units of time qualifies as future. Personally, I have a hard time to envisage what would be my research activity in 2 years. 20, it's really a lot. On the other hand, it's important to think how and performant and effective would be a future collider, which I would like to call in this context actually further in future colliders, on which we will have a number of talks, and typically very roughly, and I want to be don't want to be provocative here, one can classify them in a plane which is made on an axis of cost and the other of ambition. And here I also wanted to align the less established of all these colliders, which is the muon collider, which I personally like a lot. And it's important activity, this one of furthering future plans, but it should not obscure the fact that the future, okay, is the present, okay? The future is now, and the future is the LHC and the high luminosity LHC, right? Okay, so in this context of, in this domain of plethora of interesting things that can be done, I want to emphasize the LHC precision program, that is the possibility of experiments at the LHC to measure precisely quantities that can also be theoretically well predicted. Now, as usual, saying that one thing is interesting doesn't mean that the other things are not interesting. So we will have a lot of interesting talks and new challenges, which are not at all just a continuation of an established program, but there are plenty of programs that can be done instead in the context of direct searches that we have to continue doing and improving, and that is understood. But we also have to realize that unlike, for example, what someone could have said, I don't know, 30 years ago about the LHC can also make precision measurements because of progresses, right? Objective progress that have been made by the community in a number of items, some of which are listed here. And those progresses, must be exploited, can be exploited to make a precision program. Now, sometimes we refer to this as the standard model precision program, okay? I don't like arguing against names, and the important thing is that we do what we all want to do the same thing. However, one should pay attention to the fact that somehow within the standard model, that is to say, if you assume the validity of the standard model, all what you can do is to measure the parameters, the free parameters of the standard model, because your space of hypothesis is just made of the standard model with parameters that you want to determine, right? And this is not just to say something. The LHC has measured the Higgs mass to a precision that is more than what is needed, as far as I know, for any practical application. And there are plans to improve the measurements of the W boson mass and sin theta weak in a way that will impact already in itself our knowledge of electroweak physics. So this is a very cool thing to do. But it's true that in most of the studies, what we really want to do is to test the standard model, in which case we have to compare it one way or another with extensions of the standard model. For example, you will for sure hear about the Higgs rescaling kappa factors, the couplings of the Higgs rescaling that we do put. Those are simple extensions of the standard model, because in the standard model, the kappas are 1, so they cannot be really measured, right? And this extension, well, in a slightly more refined form at the times of LEP, it was performed, for example, by the famous electroweak precision test parameters, which are new physics accounting parameter. Given that this is the purpose, we should think to this program as a BSM precision program, in spite of the fact, actually, and this should not be in contradiction with the fact that by the precision program, one can be as agnostic as possible on the type of new physics that you expect. And for what I told you before, this is really a priority, because new physics may be something we have not thought about. So when designing the possible deformations of the standard model, you would like to compare with the data, and the proper design is essential, okay, for enabling discovery, because the data are complex. You cannot just take 1 or 2 observables and see if they fit with the standard model. The way, if you don't guess, say, wisely enough what you're looking for, you will not see it. But so you would like to model what you don't know in the way which is as agnostic as possible, but this doesn't have to go in contradiction with learning as much as possible on concrete examples of new physics, maybe addressing the same type of question: is the Higgs composite, is there a new short distance force, that so-called Z prime model? Whatever you want can be studied also directly, but it can also be studied in a sort of indirect way through some agnostic parameterization. And in this context, so the prime candidate, if you want, BSM phenomenological quote-unquote model is the effective field theory, in which you extend the standard model with higher dimensional operators. And for the rest of this talk, this effective field theory will be the so-called linear EFT. The experts know what I'm talking about, and will be truncated at dimension 6. And we will have talks about this as well, specifically to EFT, or I think also in Ramona's talk, there will be related consideration. Here it's important to me just to stress that this EFT is a model because it's the Lagrangian we use to make predictions and then to compare with the data. So for practical purposes, it's a model, but it's not the PSM target. It's not saying, I mean, instead of supersymmetry, I do EFT. No, it's not a self-standing hypothesis of new physics. It's a container. It's much more interesting. It's a container for possible hypotheses, some of which I have already thought about, some of which I have not yet thought about. And that's why we like it, because it's also agnostic with respect to what we may not have postulated, but that we will or we may discover. Now I want to further zoom a little bit in on these high energy probes, and the concept is very simple. These higher dimensional operators have bidimensional analysis in front of them a coefficient which is 1 over a scale, which is typically called lambda squared. And so again, bidimensional analysis, the way in which the impact observables is just the energy, characteristic energy of these observables, or divided by lambda squared. This coefficient, which corresponds to each given d=6 interaction operator. So at the LHC, we call low energy things taking place at 100 GeV, which is already quite a big energy, but for us it's low, at the electroweak scale, that is at the electroweak scale, in which domain you will hear for sure about the Higgs properties, okay? The Higgs kappas, for example, or translated also, as is now more and more frequently done in the effective field theory. Those are an established success that the LHC has achieved, and you will hear for sure about that. And however, the challenge associated with improving in this direction is obviously the floor, which at some point we will hit, related with systematic uncertainties, because it is true that the LHC can do precision, but it cannot do extremely precise precision. You cannot systematically measure quantities at the per mil level, because and predict these quantities correspondingly with the needed theoretical precision. Right? That's why, for example, we can study the Higgs because it was not studied before. Okay, but if we study the Z on shell, well, it's not that we can learn so much. Something, yes, but not so much, because the Z was produced and measured its properties very precisely at LEP, at the per mil level, where here we stick more like in the percentage range. The LHC offers the opportunity to measure observables at high energy, for example, at TV scale, and then simply the effect of new physics. The more you try to reach it, the more you try to approach to it, even if you don't get to the new physics scale, which will be something of the order of this lambda. Even if this lambda is above your direct reach, well, the physics decouples less and less. You have bigger and bigger effects that can overcome systematics, and so this is particularly interesting to study, especially in view of the high luminosity LHC, where if you have hidden already the systematics floor, then well, you cannot improve so easily. But instead, if you are still statistics dominated, you can improve. And furthermore, further fully exploits the key novelty of the LHC compared with previous probes, which is the fact that it allows to produce very high energy reaction, and this is what I like to call the energy and accuracy, combination of energy and accuracy frontier. If you want to be more specific and discuss very roughly what is that defines an accurate and energetic probe, okay, I would say that this could be measurements performed at 10% or better at energy of 1 TeV or more, with this following very conservative approach, that is to say that LEP, the very old E plus E minus experiment we had, I think 30 or 40 years ago at this point at CERN, was measuring very precisely, as I was saying, at 1 per mil, but was limited in energy at 100 GeV. So for example, if you have a new physics effect, a new physics operator, say here lambda, which gives a 1 per mil deformation to the physics at 100 GeV, LEP may just have missed it because it was at the boundary of sensitivity. Well, this becomes 10% at 1 TeV. And so after these thresholds, the hadron colliders win. Even in operators, as we say, or if you want observables, that are well measured by the LEP experiments. And so in this sense, so see, the topic of electroweak precision is so much dominated in textbooks now by the brilliant measurements by LEP that we all like to say that the LEC is a continuation of this LEP program. But this is not fair towards the LEC, because the variety of processes that are accessible at the LEC is so much superior to the one of LEP. And this comparison in particular only applies to few directions in the possible deformations of the standard model, to few scenarios as well, to those where LEP could even really go to 1 per mil. If I already go away from the Z pole and think to W plus W minus production, this was not at all 1 per mil, and that's why LEC can win much easily. If I think to top physics, of course, I could not do much at LEP or nothing. And if I think, for example, to the properties of the Higgs, that's unique of the LEC to characterize them. Okay, I want to just to say, this is a table with cross-section measurements at function of the mass of 2 leptons, neutral Drell-Yan process at the old version of the LEC, which was ATV. And this is to show that already back then, it was actually reached this threshold of 10% at 1 TeV. And so this reach would have been comparable to LEP, again, on specifically designed quantities that are already punished, or if you want, that are already probed very precisely by LEP. And you can also notice that when we have raised the energy from 8 to 13 TeV, the cross-section at high mass, for example, 1 TeV or even more, we'll understand more this plot in the high energy, the cross-section explodes exponentially. Okay, so the linear increase results in a reduction of statistical uncertainties, which is very significant. And so already see here that with an analysis that actually was not targeted to be extremely precise, right? Because statistics was much above at that time, can do percent-like or 3% or 2% measurements. And so projections, even taking into account conservative systematic uncertainty studies, will surpass LEP, as indeed it is the case. And this is illustrated in this plot, which shows 2 effective field theory operators written in terms of these parameters that are 2 of the electroweak precision test parameters. So this is the past. This is already what one could do with analysis that can be done with 13 TeV, and the luminosity of the LEC, and this is the luminosity of the high luminosity LEC. So you see that now LEP in this scale becomes this gray contour, and here we can be much more precise by the combination of this vertical thing and this like potato shape. We will have a quite precise test. So, so let me try to draw some general lessons of what is interesting, what is needed for these high energy probes to succeed. I think most of these things are actually needed for all possible precision studies in the EFT, including, so they extend more beyond this high energy probes domain. So we need accurate experimental measurements, but this doesn't mean that, well, experimentalists can be left alone to do these measurements, because these measurements have to be performed in the right kinematical range, and they should target the right observables. Now, until now, I've spoken only about this Drell-Yan production of 2 leptons, so there are not many observables. One can just measure all of them, but the thing starts becoming cumbersome when you go even to the next to simplest, as we will see in a couple of slides, process at the LEC. So the analysis has to be dedicated to the effect that you want to see, because one has to target the right effect, because one has to make a careful job of systematic uncertainty reduction. And also, one should not forget that there are a plethora of places where an improvement in an experiment would be a game changer. For example, in the dye boson processes, I will mention in a second, if one could do precision measurements using hadronically decay vector bosons rather than, for example, the Z2 leptons, so this would be a game changer in terms of statistics and so in terms of reach. We need accurate radical predictions, and we will have talks about that as well. Among the many things that are needed, there is specific needs that are associated with high energy probes. For example, electroweak corrections are important at high mass because they are enhanced by large logs. The parton distribution function uncertainties that you have at large center of mass energy are typically different, come from different sources, and may be larger than we have at low energy. And to the point that there is even a program that PDF experts are trying to design, in which they would fit the PDF, so the shape of the PDF, together with the EFT, such that to make sure that they get the most of the sensitivity, and of course do not fit the new physics effects when fitting the PDF. Topics related with making effective and fast enough predictions about new physics, which are essential if you want to explore this landscape of possibilities, which is characterized by these effective field theory operators. The last point is actually the first, which is you need to define targets, and that's where, so say, beyond the standard model phenomenologist can play a role which is as prominent as it has been, for example, in designing searches for supersymmetry. You have your own targets that you have qualified about retro-weak physics, and you by the EFT, and you have to identify operators that grow in which final state they grow, and if this final state can be or not measured. Then you have to characterize the effect, design possible analysis and observables, sensitivity studies, and then very importantly, assess implications, because as I said, this effective field theory should be viewed as a container of models. So we can translate on models based on what on the models, if you want, that we have already formulated, and it's a very good thing to do on top of having a table, or if you want, the likelihood in the abstract space of this effective field theory coefficient strengths, which of course are also important. Right. So I want just to flash. So again, on this Drellian, okay, not because I love Drellian, but just because so this is very simple, right? Everything is there. So you can, for example, notice the importance of PDF uncertainties, the fact that sensitivity floor is actually way below the one that we can estimate, and so allowing for possibility for progress in the future. You can notice how the necessity of, say, fast predictions, in particular by event reweighting, as needed in order to explore fully the space of possibilities. In this case, it's a 7-dimensional space. It's already big enough to make the thing not treatable if you want to make differential or fully differential analysis, for example, as in this case, if you don't have this kind of fast on top of accurate techniques. You can take your favorite model, like a Z prime, everybody's model, if you want, and compare with the reach that you have on this model from direct searches, which is this one. These are different slices of the parameter space of this model, depending on the coupling, and the one that you may get with this kind of high energy probes. And you see that there is a lot of space to gain in terms of exclusion, but also in terms of discoveries. And you see the line here that you could make for such an object at the high luminosity LAC. You can also discuss characterization, okay? You can understand what was the coupling structure of this Z prime by studying the same data. Okay, so my time is almost over. So I will just, I don't want to finish on Drellian just because that is very simple. And I want just to tell you that the next to simplest energy growing process is diboson production, and that is already much more complex. There is quite some work, and also one talk that will be on particular, I think, on this paper at this workshop. There are longitudinal dibosons, where again you can see the advance with respect to LEP in some particular plane. There is well, this is very technical for the experts concerning EFT validity, so let me skip it. There is transverse dibosons, which have complexity related with some need of measuring properly designed observables in order to address a problem of interference cancellation, including observables, and you see how much it buys you in experimental sensitivity. And all these things have been just scratched the surface, because only few channels have been studied, only very few experimental analyses exist, and also theoretical work is lacking. There has been ideas to develop in these papers here, for example, a machine learning, a complete machine learning strategy to address the EFT sensitivity in the nearly optimal way. And this plot shows how much you can gain. It's a factor of 2 in this particular case, that exploits fully the complication, the beautiful complication that there is in the many variables that control, for example, in this case is again ZW, which is again relatively simple, but still the advantage with respect to the best thing you can do with the binary analysis, or at least that we could do with the binary analysis, it's very significant. So let me go to my conclusion now. I think that there is great physics ahead of us, which of course is much broader than the specific subject I spoke about, but I think I tried to give you a flavor of many things that can be done. I emphasized the interest that there is for a combined and synergetic effort between experimentalists, QCD or electroweak calculation experts, PDF fitters, and of course physicists beyond the standard model, as we call them, to address the challenges associated with the BSM precision program, based on this EFT, which however should be interpreted for what it is, a model container inside which there are models waiting to be discovered. All this is pretty much work in progress, in the sense that there is too little experimental and also theoretical results to have a complete understanding of what are the actual perspectives. I think many of the bounds I showed you have some reason I believe are conservative, and there are many more channels to be considered just in the context of high energy probes. If you want to see an incomplete list of how many measurements, in principle, incomplete because it focuses on a particular sector, if you want, which possible measurements you can look at this paper. I didn't mention the top, but the top is very important for the LHC and for the EFT fit. And I also emphasized how, well, very briefly actually, how there could be a lot of to gain if one could, on top of making experimental unfolded measurements of distributions which are optimized and designed in light of the EFT, one could also make directly sensitivity studies at the experimental level directly on the cross-section. It's actually been directly at the ambient level, using, for example, neural networks or other sophisticated tools. And just yesterday, I've seen the first paper actually from CMS trying to do this, which I think it's great. Okay, thank you for your attention.
Okay, thank you for the very nice talk. I'd like to remind people, if you have questions, you can post them in the question and answer, which I don't see any right now, so I'll ask some questions. Andrea, are there any measurements you would like to see that haven't been done yet?
Sorry, say it again, sorry.
Are there any particular questions that you think would be, or any measurements that you think would be interesting to do that haven't been done yet?
Well, as far as I know, not even the differential Drellian charged and neutral is out yet. That's something that I was saying here, okay? This is taking 20 years because I know that the person was doing. Yeah. And recently there has been, very recently, a paper doing W gamma, and another one with full differential analysis. There has been ones doing WZ. So some of the channels that I discussed have been studied already, or some others are on the pipeline. But my viewpoint is that more and more of these are coming out. But I think we also see a lot of interest in exploring new channels, okay, like hadronic. Yeah, there is a question, it seems.
Yeah, I see a question. So it says on slide 4 or 5, could you please add a little more on the last line you added about HEP?
Oh my God. Let me see if I manage to go to slide 4 or 5 in a finite time. I don't know why the arrows do not work. I have to go with the pad.
Oh.
Yeah. 4 or 5. What should I? Yeah, what was the question? Sorry, because I cannot read it.
It says, could you please add a little more on the last line you added about HEP?
About
the previous one, sorry.
It might be the previous one.
Slide 3, maybe.
Here. You want to that I don't know what should I tell you more? Yeah. Maybe let me try to read the question. Why doesn't? Yes.
Yeah.
I don't know what is. I don't know why I cannot see the questions, and I cannot even close now the full screen, so I'm locked. No. So I don't know. Here, I just wanted to say that to me, when I was a student, I found a little bit boring this idea that I had to work and then discover the Higgs, and then I would discover supersymmetry, and then I will characterize supersymmetry, and all this was written in the stones by somebody who died before I was born. But